Welcome to this explainer. You know, if you've ever cracked open an organic chemistry textbook and felt that sudden, overwhelming wave of panic at just the sheer volume of information, well, don't worry, because you are in exactly the right place. Today, we're going to dive into the architecture of organic reactivity. We're going to completely demystify organic chemistry and show you that, hey, it's really not just some chaotic jumble of random letters and lines. It's actually a beautifully structured, highly logical system.
So let's just address the elephant in the room right off the bat. Every single chemistry student faces this one massive fundamental question. How on earth do chemists memorize millions of organic compounds? Seriously, think about that for a second. There are literally millions of known organic molecules out there. If learning chemistry meant rote memorizing every single one of them, nobody would ever become a chemist, right? The human brain just isn't wired for that kind of brute force data storage. But here's the fantastic news. They don't. Chemists absolutely do not memorize millions of compounds. Instead, they look for patterns. And honestly, this concept, it's like the ultimate cheat code to organic chemistry. Because once you stop looking at individual, isolated molecules and start looking at the underlying patterns of behavior, the entire subject just opens right up to you. It totally transforms from this impossible memorization task into a really elegant logic puzzle. So here's our roadmap for today's explainer. First, we'll cover the chemistry cheat code. Then we'll meet the functional families, go over the rules of reactivity, look at molecular interconversions, touch on some real-world applications, and finally wrap up with mastering the patterns. All right, let's dive right into it. Section 1, the chemistry cheat code, unlocking the patterns. The absolute core of this cheat code is something called the functional group. Now, think of a functional group as a very specific cluster of atoms that acts as the action center of a molecule. It completely determines exactly how that molecule is going to react chemically. So the really crucial takeaway here is that molecules with the exact same functional group will show remarkably similar chemical behavior, completely regardless of how big or small the rest of the molecule is. Look at it this way. If the carbon backbone is the noun, the functional group is the verb. It does the action. For instance, an OH group makes a molecule an alcohol, and it's going to act like an alcohol, whether it's a tiny little molecule or a massive complex one. So why does all this matter? Well, studying functional groups simplifies complex chemistry to an unbelievable degree. Instead of just guessing what a massive molecule is going to do, you just look for its functional group to predict its chemical reactions. It lets us classify organic compounds super neatly. And, even more amazingly, it is the key to understanding biological molecules. The proteins in your muscles, the DNA in your cells, the life-saving drugs in your medicine cabinet, they all operate based on the rules of functional groups. Okay, moving on to Section 2. Let's meet the functional families, the major players. First up, we've got the hydrocarbons, and it's really fascinating to see how simple bonding changes a molecule's entire personality. Alkanes, which only have single bonds, they're relatively quiet. They're mostly known for just burning as fuel or participating in free radical substitution. But shift to alkenes with a double bond, suddenly the molecule just wakes up, eagerly reacting in addition reactions. Then take it a step further to the triple bonds of alkynes, and you get an intensely reactive molecule that's ready to form these long polymer chains. The bond type literally dictates the escalating action of the molecule.
Next, let's bring oxygen into the mix. There's a beautifully logical flow here you'll see. Alcohols, with their OH group, can be oxidized into aldehydes or ketones. Oxidize them even further, and they become carboxylic acids, which are acidic and neutralize bases. But check this out. Combine an alcohol and a carboxylic acid, and boom, you construct an ester. You've also got ethers, which are generally less reactive, but can still be cleaved with strong acids. It's basically this incredible chemical ecosystem where every group is just one or two reactions away from turning into something else. Rounding out our major families, we've got the specialized groups. Nitrogen creates amines and amides, which brings basic reactions, alkylation, and hydrolysis into play. Nitriles, they can be hydrolyzed straight back into carboxylic acids. Then there's the halogens, your chlorine, bromine, and iodine, creating alkyl halides, which are these perfect targets for nucleophilic substitution and elimination. And finally, the aromatics, featuring that famous benzene ring. This boasts its own totally unique flavor of reactivity through electrophilic substitution, like nitration and sulfonation. Now let's get into Section 3, the rules of reactivity. Let's see how the pieces actually move. Now, despite those millions of molecules we talked about earlier, Almost all organic reactions broadly fall into just 4 categories. Addition reactions, where you're literally adding atoms across double or triple bonds. Substitution reactions, where you simply swap one group out to replace it with another. Elimination reactions, which are exactly the opposite of addition, you're removing atoms to form a double bond. And rearrangement reactions, where the molecule simply reorganizes its own structure. Honestly, every complex synthesis you have ever seen is just a massive combination of these 4 fundamental moves. But how do these moves actually happen? Well, it is all a game of electrons. Nucleophilic reactions feature an attack by electron-rich species that are basically out hunting for a positive charge. Electrophilic reactions are the reverse. That's an attack by electron-deficient species desperately hunting for electrons. And free radical reactions involve these highly reactive species with unpaired electrons. Basically, if you can understand who has the electrons and who wants them, you can predict exactly where the attack is going to happen. Also, one of the most absolutely vital rules of reactivity you need to know is the seesaw relationship between oxidation and reduction. It's a perfect balancing act. Oxidation is the gain of oxygen or the loss of hydrogen. Reduction is the exact inverse, the gain of hydrogen or the loss of oxygen. Definitely keep this rule in your back pocket because so many of the functional groups we just talked about interconvert by simply sliding back and forth along this redox scale. All right, let's keep moving. Section 4, molecular interconversions. This is the ultimate blueprint. Okay, so here is where the magic really happens. As we said, chemistry is just moving pieces around a board. Let's walk through this a bit. Say you start with an alcohol, apply some oxidation, and boom, you transform it into an aldehyde. Take that exact same aldehyde, apply a little more oxidation, and it becomes a carboxylic acid. Now, react that acid with an alcohol in a process called esterification, and you've literally built an ester. Or, start somewhere else entirely. Take an alkene, add water through hydration, and you've just created an alcohol. Adopting this flowchart mentality really proves that you aren't just memorizing isolated facts. You're learning the actual pathways to turn any functional group into any other functional group.
Which brings us to Section 5, real-world applications, and why all of this actually matters. It matters because this chemical language literally dictates our entire physical world. Take medicines. It's the specific functional groups on a drug molecule that determine how it binds in your body to cure a disease. In material science, functional groups are what allow us to string molecules into massive polymers, giving us things like plastics and nylon. In food chemistry, they are the actual flavors you taste and the preservatives that keep our food safe. And in biochemistry, the enzymes digesting your lunch and the DNA storing your genetic code are entirely governed by these exact same functional group interactions. It's everywhere.
Wrapping things up with Section 6, mastering the patterns, a strategy for students. So to the students out there, please stop trying to memorize the whole textbook. Just follow these 4 simple steps instead. 1. Learn your functional groups first. They are the alphabet of organic chemistry, period. 2. Focus entirely on reaction patterns, not blind memorization. 3. Practice the reaction mechanisms so you actually understand why the electrons are moving the way they do. And 4. Use flowcharts for conversions. Literally draw out the maps of how one family turns into another. Study smart and let the underlying structure of the science do the heavy lifting for you. I really want to leave you with this final, incredibly powerful insight. Look, organic chemistry may seem vast and super intimidating at first glance, but it is deeply, beautifully pattern-based. Once you master functional groups and their reactions, you literally unlock the ability to predict and understand almost any organic transformation in the universe. It honestly ceases to be magic and becomes a language you can fluently speak. So my question to you is this. Now that you finally have the cheat code, what molecular transformations will you decode next? Thank you so much for joining me for this explainer, and remember, keep looking for those patterns.